I think this is a really good place to leap off and do our next thing, okay? Which is, you asked me, what happens when we swap these two, right? Swap that around, okay? I want you to look at this again. So now, I'll make a new subheading, okay? I'm going to give it a name in a second, but I want to look at what the maths is first. We looked at this, right? You took these two, right? By the way, they're called variables. Let's just label those. You took the variables and you swapped them, and then you got this shape. Well, there's something else you can swap here as well. Actually, there's a few different things. The thing we're particularly looking at this morning is, see these guys on the right-hand side, x and 2, x squared? What happens when you swap those? Y equals, not x to the power of 2, 2 to the power of x. Now, this is interesting because it looks, well, the numbers look different to what we've got over here, right? They're rearranged differently, okay? But actually, we've looked at these things before. We did a whole topic on them underneath algebra, right? When you've got things up here in the power, we called these indices. Do you remember that? Yeah. Indices? It was called an index, a power. There was one more name it had, the most unusual name, the most uncommon one, but I told it to you back then. It starts with an E. I told it to you back then specifically so that this title would make sense. Does anyone remember what the name was? E for, see the problem is we almost never use it, right? It's E for
expanding.
Exponent.
Exponential.
And the reason why it's useful to know they're called exponents is because these graphs are called exponential graphs. Right? Now we've actually, even if you don't know much about the maths of it, which we're going to explore in a second, right? We actually use this language. We use it all the time. We say something grows exponentially, which means, is that slow or fast?
Fast.
That's fast. It's really, really fast. Okay. It means it doesn't just grow like this. This grows, but it grows faster as time goes on. It gets steeper and steeper and steeper and steeper.
That's a finance man.
So here's my question. Just like if you got a piece of sheet music and you said, okay, well I guess if I can read this, then I can play it and see what it sounds like, right? Hear what it sounds like. What does this look like? We know what all of these look like. What would it look like? There is a button on your calculator for it. We have a tool for working out what things look like when we have no idea any information about them. What was our tool that we keep going back to over and over again? Do you remember? Are you going to answer something else or this question?
I was going to answer that.
Yeah.
Does it start at one point and then just drifts off?
Well, it is going to go really high, but my question is, how high is it going to go, right? And is there anything interesting, right?
There is no...
Do you remember this guy? Remember this guy?
Oh, that guy.
The rectangle.
Oh, that
This is a table of values, very good.
X and Y.
You take X and Y values, right? And then you try some and you see what happens, okay? Now, do you remember with the parabola what we did was, we tried out -2, -1, 0, 1, 2. Whoops, sorry.
Oh, we tested them all out.
Yeah, we tested out numbers, we saw what happened. When we tried these out, I'll just refresh your memory, we got these numbers, 4, 1, 0, 1, 4. Right? You know, we said, oh, it's like a palindrome. It's mirrored, right? And that's why these shapes are mirrored. Okay? Well, let's see what happens with these guys. In fact, I got 1, 2, 3, 4, 5, 6. Let's have -2, -1, 0. Let's try these values. Let's give them a go. In order to get an accurate picture of this, okay, you need to remember how indices work. Remember? Indices, that's plural, powers, exponents, they're all the same thing. Okay, so let's just do a few numbers first. Do you remember, let's go with a simple example. Something like, say, 3 squared, 3 to the power of 2. What does that mean? What's that short for? It's an abbreviation. Good, 3 times 3, which of course is 9. No problem. I'm not going to write that down though because it's trivial. If I were to say, make it a bigger number up there, 3 to the power of 5. What's that short for? Okay, 5 times. You get the idea. Okay, good. So therefore, right away, just off of this, straight away we can fill out 1, 2, 3 values. Okay? This is y equals, not 3, but 2 to the power of these numbers here. Okay? So if x is 1, then this will be 2 to the power of 1. 2 to the power of 1. That's just 2. Okay? Then 2 to the power of 2 will be 4. Now careful. 2 to the power of 3, right, would mean I should do 2 times 2 times 2 again, and that's 8. Right? Okay, now have a look at this, right? From here, you can kind of follow a pattern if you can't remember this, right? Look at these numbers. We went from left to right, but what if you went in the reverse order? If you went from this to this, what have we done? You've divided
Basically
8.
halving it.
You have halved it. That's exactly what I've done. 8 to 4 is half. 4 to 2 is also half.
And then you
So
do
2 should go to,
1.
when you halve 2, you get 1.
And then when you halve one
And then you
half,
should halve again. You should halve again.
half of a half is a zero.
And then you should halve again.
Yes.
Okay? Alright, now.
And there's 1 x.
Shh.
Wait, so what happens if you put 0.5 and 0.25 down?
That's okay. Now, notice this with me, please. We were just going from right to left, okay? So you keep halving, okay? And so if I went from left to right, instead of halving, what's the opposite of halving?
Passing.
Doubling. It is adding stuff, but more specifically,
Yeah.
right? It's okay. Double.
It's not addition.
Okay, so
Yeah, it is.
first question. How far do I go till I hit like a maximum? Right? Till I hit a point where I have to stop.
12.
What does that mean? Infinite.
Just means that no one's
It means I can keep on doing this. There's no limit to this. Well, let's just think about this. I don't have to draw the whole rest of the table, right? What would happen if you halved this number? If you halved a quarter, you'd get an eighth. What would happen if you halved that? A 16. If you halved it again?
32.
Okay, and you can start to see, hold on a
Oh,
second.
wait, you can.
And in fact, just look, pay attention to these denominators. Pay attention to them. If I went over this way, you double 8, you get 16. And then you double that, you get 32. You 64. In fact, you're getting exactly the same numbers here, but they're, this is a numerator, and these are denominators, right? So these things are all getting smaller, and these are all getting bigger. But if you can go that way forever, you can also go this way forever. Okay, now, question. How far would you have to go to hit 0? Because these are getting really small, right? If you put this into your calculator, it's a pretty small number.
You're never going to hit 0.
Wait. Hold on. Never hit 0? Are you sure? These are getting... Like, you can pop this into your calculator. This is going to be 0.0 blah, 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 blah. It's a tiny number.
Doesn't matter. It's never going to hit 0.
Why not, though? So pairs onto something. Why not?
It's not.
Can we try? Because this is really important. In maths, you don't just say, okay, that's the answer.
You can't.
It's all about why is the answer what it is. Okay, Ali?
Like, if you continue that way, because like, you don't get to 0. So maybe like, you won't get to 0 the other way.
No, a number divided by 2 is never going to be 0, I think.
Okay, that's true. Wait, hold on. A number divided by 2 is never going to be equal to 0. So let's picture this. I guess it's a little bit like you've got a cake, right? And then you slice it in half, and then you've got 2 halves, right? And then you take the halves and you slice that, you know, with a quarter, and you just keep on slicing, right? Now here's the thing: with a cake, eventually you must stop. You will run out of cake eventually. It will just become like a mess on your plate, right? But this is more than just cake. These numbers, right? They really can go forever, right? And you will never ever get to 0. You'll get some very, very small numbers, okay? But you'll never reach there. So therefore it follows at the same time, see these numbers, how they're all positive, right?
Yes.
So how far would I have to go to get a negative?
What do you mean?
Like, can I halve a certain number of times and get a negative number somewhere over here? No, I can't, for the same reason that I can't get to 0, right? No matter how many times you divide, you're never going to get an anti-cake, right? You just get no
Oh
cake.
yeah, because like negative comes off to 0.
So therefore, all these numbers are positive.